Okay, so uh, the point of the matter is that when we use FFT function, uh, what actually we are doing is called discrete Fourier transform. The input to the discrete Fourier transform is some number of samples, some capital N number of samples. Those samples are in time domain. And because of that time domain, the frequency, because of that sampling operation that has already been done in the time domain, the frequency is become periodic with a period which is equal to the sample rate f of s. So far so good. But the other part comes that not only that the time has been discretized, and because of that the frequency domain has become periodic, but also that we need to discretize that periodic frequency axis as well, because this algorithm cannot evaluate continuous valued frequencies, because there is infinite number of uh, continuous the infinite number of values that the algorithm will have to compute, which is not feasible. So we are forced to discretize the frequency axis because we are working with a computer. As soon as we discretize the frequency axis, the implication is that we are assuming that the time domain signal is periodic. And the period in time domain is inverse of that discretization that we did in the frequency domain. Alternatively, when we take the DFT of n samples, effectively we are discretizing the frequency by uh, inverse of that n samples effectively. Uh, so, um, so that is the underlying assumption behind discrete Fourier transform. Now, the discrete Fourier transform then eventually uses the same formula as the DTFS, discrete time Fourier series formula, which is given by this equation here, equation number 2, or this equation number 1. This is the formula for discrete time Fourier series, which is applied when this W of n is periodic with capital N samples. In our case, those n samples may not be periodic, and so there is a limitation of DFT. The presumed periodicity may not actually be the reality. Okay, so that is pretty much it. The reason why this discrete Fourier transform has become very popular is because of that fast Fourier transform function. I think it was invented in 1960s, and the opinion is that the invention of that fast Fourier transform actually brought about a paradigm shift in our day-to-day technology. A lot of our technological products may not be feasible if this DFT was not invented, because otherwise the computations required were simply too much. But this FFT function, especially when n is a power of 2, is actually very highly efficient implementation of this discrete Fourier transform. Okay, so now with that, let us go back to the questions that we were looking at. So the first question is that why we need to divide the output of the dot product by n sample. Actually, the question should be that why even there is a dot product. So the answer to that first question is that if you look at this equation 1, or equation 2, both are the same. You can think of this W as a vector of capital N samples. And similarly, you can create a vector of this complex exponential with integer value k. Then you will see that this summation here becomes a dot product of those two vectors. And that dot product has to be divided by n. And so the answer to that first question is that equation 1 can be written as a dot product W with E of k, and this 1 over n is present there. Okay, why do we take the range of f cycle set as going from minus fs over 2 to fs over 2 with n sample elements? Well, and why do we use the Fft shift function? So, as I said earlier, Matlab's Fft function assumes that the base period is 0 to f of s. Our my Fourier transform takes it to be minus fs over 2 to plus fs over 2. So when we take it from minus fs over 2 to plus fs over 2, we get this as the f cycle set. Otherwise, we get the values of k that go from 0 to n minus 1, where 0 corresponds to 0 hertz, n minus 1 corresponds to the sample in the frequency domain just prior to f of s. This is Matlab's Fft implementation. My Fourier transform function makes use of k, which goes from negative n over 2 to n over 2 minus 1. Now, why do we need to use Fft shift function? Well, this is a property of Fourier transformation that we have maybe not paid too much attention to it, but I had given you this as a reading assignment, that if you have a real valued function in the time domain, its Fourier transform is symmetric around 0 hertz. Now, a lot of the times when we take Fourier transform either through Fft or through my Fourier transform function, we want to look at this symmetry in the frequency domain around 0 hertz. Maybe it looks like a rectangle, or it looks like a triangle, or maybe it looks like some type of parabola or something like that, the Fourier transform. And that symmetry you can see only if the range is minus fs over 2 to plus fs over 2 with 0 in the middle. Whereas if 0 is not in the middle, 0 is at the beginning, then although that symmetry is there, it will appear strange. And so that is what the Fft shift function does. It converts the range of 0 to fs, that the values that are evaluated over 0 to fs, they get mapped to minus fs over 2 to plus fs over 2, so that the plot looks nice, it looks symmetric. Symmetry is always there, it's just the way the plot gets exhibited. The visual aspects of it become better by using Fft shift function. And then the last question is, why does the output of my Fourier transform differ from the one obtained using Matlab's Fft function? And that reason I have already told you that in my Fourier transform function, that variable k, which has to be an integer going from 0 to n minus 1, was not actually, first of all, it was not an integer, and secondly, it was going from 0 to n, not 0 to n minus 1. And so uh, our TA, Bibin, has posted an announcement on our Google Classroom where you were asked to make a small change in this my Fourier transform so that the variable k goes from 0 to n minus 1. I mean, the values that it takes are from 0 to 0, 1 up to n minus 1, um, except the actual values might be going from negative n over 2 to positive n over 2 minus 1. In any ways, the values of k are integer valued after you make change to my Fourier transform function, and then once you make that change, its output and Matlab's output will be identical. So that is what is shown here, that if I use the current implementation of my Fourier transform, the value of k goes from 0 to 5 when capital N is 5, and the values are not integer. But after making the change that the TA has suggested you to make, k goes from 0 to 4, and the values are now integer valued. Okay, so that concludes the response to the questions that were asked out of Lab 5. Very good that you asked those questions. I think, I hope that my explanation has addressed your questions and doubts. And so very good. I think I'm happy to see that you have made good progress on Lab 5. The last topic that is remaining is the topic of modulation and quantization, and I'll be uploading some videos on that topic maybe either today or at least by the weekend. Okay, see you then. We will actually have one more lab on that topic of modulation and demodulation starting probably next week.